What's up, wonderful fans? Welcome back to the crazy world of Hulseyville. This is Mr. Hulsey. I am really getting close to PewDiePie here in sub count. So don't forget to hit that like button, smash that subscribe button, and don't forget to ring the bell so you're alerted to all my latest updates. All right, let me minimize this a little bit and move it over here. Oops, I might be covering up my ad supporters, but that's all right. So this lesson is about tolerances in dimension drawings. So this is, don't forget in your notebook to put 7.3 tolerances. Here's the STEM news for today. A robot basketball player. I think you'll like it a lot. Jump over to this presentation on Schoology so you can look at this video. It's pretty cool. Shoots free throws every single time. Before you come in, do all these things like before. Announcements. I don't have anything new. Uh-oh, my baby is 1 now. As you're watching this video, his birthday is on Thursday, the 11th. So tell him happy birthday. In the comments section, in the doobly-doo. So today's agenda, you guys already know that. Let's talk about tolerances. What are they? Tolerance is the acceptable amount of variation, a dimensional variation, that will still allow an object to function correctly. So we want to say how much tolerance we can have because there will always be some variation. No matter how good your machining equipment is, your part after it's manufactured will always deviate a little bit from the target dimension. But this tolerance, when we specify it, it's the amount of acceptable variability because we know there is going to be some due to random errors and systematic errors sometimes. But we know there's going to be some. We want to say, what's the tolerable amount? Okay, one quick note, don't specify a tolerance that's smaller than necessary because as tolerance gets smaller, or in other words, as we want our part to be more and more precise, our dimension to be more and more precise, that hikes up the cost. Because, really for two reasons. For two reasons. You will need more precise manufacturing equipment, A, and B, you will have to toss out a lot more parts that don't meet those requirements. So that would drive up costs. Okay, ANSI and ASME collaborated on this standard. They said each dimension shall have a tolerance. Normally, if you don't have a tolerance, that's a general note. That's a general tolerance. We'll talk about those in a second. Types of tolerances, write these three down. Limit, bilateral, and unilateral. And we have an example of each of these here. This one is limit dimensions. This one is limit dimensions. It tells you exactly what the limits are for your dimensions. It doesn't tell you how much it can deviate or the variation, but it tells you what those upper and lower limits are exactly. This over here is a bilateral tolerance because it's the same on either side of the target, and this one is a unilateral tolerance. It says it cannot go any lower than this target. It can go above though, so that's a unilateral. Okay, first one, limit dimension. Like I said, it gives you the upper and lower limits. That might be handy if you have some tolerance that is bilateral but not even. That might help. Okay, also if you have let's see, I skipped one. Here's bilateral tolerance. It's a plus or minus sign, and then this says the counterbore depth can be 0.003 or 3 thousandths. When we talk about really small measurements like this, we often say thou, short for 1,000th of an inch. So 3 thou, larger or smaller than a 1/4 inch. Okay, and then obviously the unilateral is next. We like to say, if it's a plus here, it can be larger, and then -0, that means it can't be any smaller. You can do it the other way around. If you want it to be a certain height, a certain large size, then you would say +0 and minus whatever you want to say there. Okay, there's the first question. Which type of tolerance is this? Should be a pretty straightforward answer. Yeah, it's this one, unilateral tolerance, because it can't go lower. What's this one? This one is a bilateral tolerance, plus or minus. So what's this one? This is the limit dimension. Okay. Terms related to tolerance, we say that a part is out of tolerance if we say, for instance, that we want it to be 1/4 plus or minus 5/100ths of an inch, 1/4 inch plus or minus 5/100ths of an inch. That's a really big tolerance, by the way. But if we say that and then we get a part that's 0.1 inches, that's out of tolerance. That's out of that tolerant range right there, the tolerant range. Okay, here's a specific or specified dimension that's also called the target dimension. as I was saying before, specified dimension is what we're shooting for. Okay, that's the target, what we're shooting for. And then limits, upper limit and lower limit. We can calculate that with these equations. You can write these equations down, but I think you kind of get the idea. I don't think that's necessary or essential to write these down. There's one style or one type of dimension that already says these explicitly. It leaves out the variance, and that is the limit dimension. So the limit dimension, you don't have to calculate anything to get upper and lower limits. They're already there. It's just that there's no specified dimension. Okay, tolerance itself can be calculated. So tolerance, if you say the tolerance of this dimension is something, then you have to give a number. And that number is the size or the range of that interval. Okay, it's the size or the range of that interval, the total variance. So I would write this equation down just so you don't forget. Upper limit minus lower limit. You can also say tolerance equals positive variance plus negative variance, the absolute value of the sum, or you could say absolute sum of positive and negative variance. So the sum of the absolute value of positive and negative variance. So if you have a unidirectional, let me go back up. If you have a unidirectional tolerance like this one, your positive variance is 5, your negative variance is nothing. So the sum, the absolute sum of those is 5 thou. And that would be the tolerance. The tolerance here is equal to the positive variance. Okay, here's a good picture of all of it put together. If you have a plus or minus 5/100ths, 0.05, so the lower the negative variance is 0.05, the positive variance is 0.05, the lower limit is 1.55, the upper limit is 1.55, and you can subtract the two and get tolerance. You can also add the absolute value of the positive variance and the negative variance to get the same thing, 1/10 of an inch. Okay, here's another thing. General tolerances, this will save you a lot of time. It just says if you have this many significant digits or this many decimal places, if you have this many decimal places, this is the tolerance always. Because it's not really necessary to give a different tolerance on every single dimension. You just say, hey, if it's specified at this dimension, then this is how precise I want it to be. Yeah, here's an example of a general tolerance, 3.00. You would look down here to your general notes here. I have 2 decimal places, so this is my bilateral tolerance here. Find me the upper limit and the lower limit. Yeah, pretty easy. You just add the positive variance or subtract the negative variance. So you have 3.01 and 2.99 for the upper and lower limit. Now find me the tolerance. Pretty easy, is just subtract upper and lower, and you get this 0.02. Here's a shortcut. If you have a bilateral tolerance, you can just double it. Bilateral tolerance, you can just double it to find the numeric value of the tolerance. Okay, another note, don't specify dimensions only to precision and tolerance necessary. Like I said before, if you specify a tolerance that's too small or too tight, too precise, you will hike up your costs unnecessarily. So let's talk about allowance. This is a totally different concept. This is basically tolerance between 2 different pieces. If one piece is going inside another piece, if one part is going inside another part, you talk about allowance. And this is sort of related to tolerance, but it's more on purpose, and we'll see kind of what that means in a sec. There are 3 types of fits. Write these fits down. 3 types of fits: clearance, interference, and transition. Clearance is there will always be a clearance, or there will always be a gap between whatever you're putting, the thing that's going in and the thing that's going into. In other words, axle and opening. There will always be a gap between those. And if you look, you can tell, because if you look at, let's see, if I want the gap to go away, I'm going to make my, is that the right way for you? Yeah, this is better. I'm going to make the axle as big as possible. I want to check to see if there's any configuration where that gap will actually go away. So I can make this part, the axle part, as big as possible. That would be that 10 inches flat. And I can make my hole or opening as small as possible. That would be 10.15. Okay, so great. Even if this is as big as possible, even if this is as small as possible, it'll still fit with some clearance. That clearance there is going to be that 0.15. Okay, interference fit is the opposite. No matter how small your axle goes, you want it to be as small as possible, and you want your opening to be as big as possible. No matter that configuration there, you'll still have some interference. And that's okay. It looks weird in Inventor, like a part going inside another part. I'm sure you've seen that before, like the two materials actually, just phasing through each other. That doesn't happen except for quantum tunneling, but we're not talking about quantum. That doesn't happen in real life. What would happen is your parts would actually squeeze together. You actually compress those parts, especially with plastic. Plastic is more pliable or more compressible or more compliant. Compliant is a good mech engineering term. Compliant, so that it will squeeze into the opening here and it'll stay stuck in there. That's how parts actually work. They change dimension as you shove them in somewhere. So there is always interference, even if we make this as small. Let me think. So there's always interference. Even if we make this as small as possible and we make the opening as big as possible, it's still going to interfere. So how small can it get? 9.92. How big can this get? 9.90. So there's still some interference, and that interference is calculated to be 0.02. Okay, and then the other type of fit, let's go back. This is transition fit. That is if you do your different conditions, like maybe a very small axle and a very big opening. There might be clearance there, but if you change it, a very big axle and a small opening, there might be interference there. Okay, so that is all about how you specify those tolerances and those conditions. So to do your calculations, you have to do this crazy thing called a maximum material condition, MMC. It's not that hard if you really think about it. The MMC is the situation after your tolerances have been specified, situation of manufactured parts. That's the huge difference here. We're talking about manufactured parts, not dimension parts that we're hoping to manufacture in a little bit. We're talking about already manufactured parts. Maximum material condition is inside your tolerance range. An axle, which is going into an opening, an axle, if you want it to use the most material possible, it will be as big as possible. So the axle will be as big as possible, okay? And then if you want to use more material on a hole or opening, the hole will be as small as possible, all right? So that's the maximum material condition. Least material condition is the opposite. If you want a hole if you want an axle to use the least material, you make the axle small. If you want a hole to use the most material, you make the hole big, because the material around it will be lessened. At least material condition. Okay. And then we talked about clearance and interference. Allowance, definitely write this down and the equation for it. Allowance is the minimum clearance or maximum interference between parts. Minimum clearance or maximum interference. So we'll calculate that in a sec. It would be the MMC internal, so a big internal feature, and the MMC external, a small external feature, a small hole. Big part going into a small hole. So here's an example of calculating it. MMC internal minus MMC external. So we look at this this axle going into the hole. MMC for the axle is very, very big, as big as it can get, 10. And the MMC for the hole is as small as it can get, 10.15. We subtract those and we get a 0.15. So there will be a clearance here. This is a clearance condition. This is a clearance fit. No matter how big our axle gets and how small our hole gets, there is still a lot of clearance, and that's the minimum clearance, right? Because we can make the difference even bigger. But with MMCs on both of those, we get that's the minimum clearance. The allowance is the minimum clearance, is 0.15. Okay, let's calculate the allowance for this part right here. I'll give you a hint, this is an interference fit. Okay, so you take the MMC external, which is as big as it will get, 10.0, and the MMC internal, which is as small as this hole will get, which is 9.85. Note, earlier I calculated the minimum interference. So I calculated, when I was trying to see if it was an interference fit, I looked at the 9.92 and the 9.90. And I said, well, even if we make it the minimum interference possible, it's still going to be interference and not clearance. That's why I calculated that earlier. But when we try to find allowance, it's different. We're finding we're doing MMC on both. Which would give us a 0.15 allowance, 0.15 inches for allowance. So this tells us if it's negative, this tells us interference. If the allowance is negative, it tells us interference. So allowance is important because we want to find the definition of allowance is minimum clearance or maximum interference. Minimum clearance or maximum interference, which is that MMC condition. And that's going to be important because that will tell us if, according to our tolerances, we will ever get two parts that won't fit. Okay, if we will ever get two parts that won't fit. So if our allowance is too big, then parts that are not out of tolerance will still not fit. Parts that are not out of tolerance will still not fit with each other. That's why it's important to specify what allowance we're talking about and make sure that it's low enough. Otherwise, our parts will not fit together. If the clearance is very, very big, in other words, if this allowance ends up being a big positive number, those parts will still fit. Maybe they'll slide out of each other, but they'll still fit. So allowance, that's why we talk about MMC and not LMC when we're calculating allowance, because in this situation, we don't really care if they're going to slide out. We care if they will fit or not. So it's important to specify allowance. Okay, I'm going to talk about the assignment now. The assignment is pretty much straightforward. I'm going to talk to you about question 1, which goes over Inventor details. At the very bottom of the assignment, before the conclusion questions, it'll tell you how to do this step by step, but here's the video part of it if you want. Right-click on a dimension that's already there and hit Edit. This menu, the same menu that's precision and tolerance, not text, but if you go over to the precision and tolerance tab first, this menu will pop up every time you add a new dimension. So that'll make it really nice to add these tolerances as you go. But yeah, symmetric is the bilateral, deviation is the unilateral, stacked would be your limit dimension. So you can type in those numbers here, and then when you're done, hit OK, and it'll come up just how you want it. So make sure your tolerances and your dimensions, your tolerances on your dimensions are exactly where they need to go according to the assignment. For a whole note, it's a little bit different. Right-click on the whole note, hit Edit Whole Note. Then there's this menu that looks different. Click on Precision and Tolerance. And then yours should look like this because this is the default. I expanded the advanced options here. You don't want to use the global precision, so uncheck global precision. Then you can edit the tolerances for every dimension that's included in this whole note. So if you check on this, then you have symmetric, deviation, and limits, stacked limits like we had before. That's about it there. But for the general tolerances, it's a little more difficult. Hit General under Annotate tab and Table panel in the ribbon. Then let's see, we want a 2-column and 3 data row table. Let me go in and make sure, there we go. I added a little table for you, a little view of the table from the assignment. So 2 columns and 3 data rows, hit OK, and you can place it wherever you want to. Now we'll have to edit that table. And it's kind of a pain to go in here and change all of the details of the table, but that's how we go. Table layout. We want this to say general tolerances in all caps there. Hit OK. And then for the columns, this is the biggest pain here. Yours should be clear over here, but you want to remove these 2 columns. And then you want to add new columns. Click here to add property. We want to say linear dimensions, and hit OK or click Enter. And then we also want to say angles. But I think I did them backwards. Yeah, linear dimensions should be moved up. Okay, then you hit OK, and you see them both here. If you click, if you hit Apply first, now you can edit the text. And this is going to be x.xx equals, x.x equals. And then this plus or minus sign, it's really in the table here. Let's grab that, and then we can paste that in. That's a little bit better. Okay, and then for angles, we can add this text down there. I think that looks better. If you want it to be sized properly, you can resize it. I don't know why it goes away, but you have to paste it in there. I'm using Control-C and Control-V to paste, by the way. If you run into some issues here with some formatting, which you might if you don't type in x.xx and all this first, then you can just go back and mess with the formatting yourself. It's just a little weird. It's not a very good text editor. But this is the this is the table that you want. Oh, it's still not sized correctly, so you can just click and drag it there. That's the table. That's good. On this, don't take a screenshot of this because it's not finished. I don't have the dimensions here. Do this on your own and take the screenshot. The rest of the assignment is a little bit of critical thinking, but I think you can do it. Good luck.